So we continue with the Sierra sample data set for Brazil. And the topic of this little demonstration is unique values maps and collocation maps. Now, unique value map is just a categorical map. You know, you can do this in a lot of different things. Collocation map, I'm not aware of that being in anything except GeoDa. I mean, there's a lot of copycats, so maybe by now it's in other things too, but a collocation map allows you to do what I call map algebra. And I'll show you in a second what this is useful for. So I'm going to make two unique values maps. We already saw last time how you can save the categories from any map as a variable, a categorical variable. And then you can use that in a unique values map, but it doesn't look that great, right? Doesn't show any gradation, no sequential legends or diverging legends, it's just a bunch of colors. But for binary variables, 0, 1 variables, this is very useful because it shows you where the ones and the zeros are. And as always, our point of departure is that there shouldn't be any rhyme or reason to these. They should be just mixed together, like what we saw with the shuffle command the other day. You just mix them together. The values don't change, but where they are changes. So point of departure is it doesn't matter. We go to the map icon, and we've already done this. We pick unique values map, and then the variable list, we go all the way to the bottom, and you have two here, Zika D and MIC D. Zika D is a dummy variable, 0, 1 variable for the occurrence of Zika, and MIC is microcephaly. These are two mosquito-borne diseases. So you would expect a priori that the patterns are the same if mosquitoes are in the same place, right? So the other one, same thing. You go down to unique values map, all the way down to MIC D, and you create the map. So these two maps, the question is, to what extent does this overlap? So you see, for Zika, there's 32 municipios that have presence, and for microcephaly, there's 54. A natural question is, where does it occur in both maps? So that's a simple logical question. You know, it's an and question, one here and one there. How do you do this visually? Before I go there, let me show how you can make this look better. And that doesn't work yet on the web version. If you right-click on the little rectangle, we're going to change the fill color for 0. We're going to make it white. So we click white and then close this. And now it's not 2 shades of blue. Do the same here. Right-click on the rectangle, fill color, white, and close. One thing we could do, we already saw this, is we could select the ones in, say, for Zika, and we can do this by just clicking, not right-clicking, just clicking on the little rectangle with a value of 1, and this will select the ones in the Zika map, and also through linking the ones in the other map. And what we see in the other map is that some are dark blue in both, some are white in one and dark blue in the other one, and vice versa. So you can do this from both ends. You can do this on this end as well, but it doesn't give you really a clear picture, and visual impression can always be misleading. You have to start counting them, right? Never do that, okay? I never do it because I always make mistakes, and then you have to count multiple times until you start getting the same number, right? Don't do it. Instead, what we're going to do, I'm going to unselect, is I'm going to show you this collocation map. So we go to the map toolbar thing again, and we go down to right below unique values map is the collocation map, and you pick that. And that allows you to select variables. And what it's going to do is find the matches. And then it's going to give you 3 categories. The ones where the ones match, the ones where the zeros match, and the ones where there's a mismatch. So that's a simple logical operation. This is called map algebra. This is used a lot in remote sensing data, not so much in polygons, but gridded data, pixels, pixel manipulations, games. Some of you may be, well, I know players of games, but maybe also developers of games. There's a lot of pixel manipulation going on in these games, and it's always the same logic. These are matrices. So we picked Zika D, and then also microcephaly. And you can pick the kind of color scheme that you want, but obviously for this one, unique values is the only one that makes sense. And now if you click on OK, then you see 3 different colors. You see there's 17 places that match in both. So if you click on the little rectangle, you select them in all 3 maps, and you see they're dark blue colored in all 3 maps. We can get rid of this. Okay. Then the light blue ones are the ones where the zeros match. So these must be white in both maps. And then the others are the ones where there's a mismatch. So these are either blue in one map and white in another, or vice versa. So this is a very simple logical operation that shows you whether there is overlap or not between these 2 cases of binary variables. And then, of course, the statistical question is, to what extent is this random due to chance, or to what extent is there, dare I use the word, clustering going on? Okay. And I don't know if I'm going to get to it in this class, but you can definitely explore it. It's in the GeoDa book. There's formal measures of clusters of 2 binary variables, the extent to which they overlap and their neighbors overlap, very importantly. Okay. So this is the collocation map. It's a very easy tool to use to find overlap in space between interesting categories. For example, you can apply this to, after you get to the cluster analysis, we make what is called cluster maps, which identify locations of clusters for 2 different variables. And then you can do a collocation map between the 2 cluster maps, which shows you what locations are in clusters in both maps. These are the kinds of questions you address with this.